All right, so today we're going to be talking about synchronous generators. And so the first thing that we're going to talk about is their construction and operation. So we're going to have something like this. I'm going to start with our stator once again. So this is another example of a cylindrical machine. And the stator that we're going to have here is, essentially the exact same thing we would have had for our induction motor stator. So we are going to have some A phase winding here. I'm going to label this as A, and then 180 degrees across from that is going to be our A prime. I'm just going to make a little note here that this is a phase winding. And then 122 degrees out of phase, 120 degrees out of phase with the A winding, we're going to have our B. And then 180 degrees from that is going to be our B prime. And then lastly, over here, we'll have our C and our C prime. Okay. So for whatever reason, the stator is often also referred to in a synchronous machine as the armature. So I'm just going to put armature or stator here. I will refer to it as the stator for what it's worth. So this is our stator system. It is identical to that of a three-phase induction motor. Where things are going to get very, very different is what's going on with the rotor, okay? So our rotor is going to look something akin to this. Imagine I could draw well. So we're going to assume it's spinning in a counterclockwise direction. This kind of central thing right here is our shaft. And then we have what is essentially an electromagnet here in the middle. So I'm going to have a north pole and a south pole. These are are known as our field poles. They are excited by a DC current in the field winding. And then what I'm going to try to draw here is our field windings. And I'm going to draw these a little bit differently. So we're going to have specific windings on our rotor. Like so. These are excited by a DC current applied through slip rings. And then this whole thing together is what's known as our field system, or more commonly, the rotor. Okay. So what we have essentially is a DC electromagnet that is our rotor that is spinning inside of a three-phase stator. Okay. So we're talking about generator operation for right now. So essentially, our rotating magnetic field in our generator operation is going to be because our rotor looks like an electromagnet and it is spinning around. So that is where our rotating magnetic field is coming from, is literally us spinning our electromagnetic rotor. And because we have DC excitation, the amount of field that's generated by that electromagnet is going to be a constant thing. Okay. So let me write that down for you guys. Where B rotor is constant, spinning inside a three-phase stator, which is constructed similar to that of an induction motor. If a field current I sub F flows through the rotor windings, and the rotor, is driven counterclockwise by the prime mover. So the prime mover is literally just the mechanism that allows us to spin the rotor. A revolving magnetic field will be established in the air gap. This rotating magnetic field will vary the flux linkage seen by coils A prime, B prime, and C to C prime. So essentially, as this magnet spins, the amount of flux, magnetic flux seen by each coil is going to change, right? So like the way that I have it drawn right now, we would see essentially no flux whatsoever through the A coil because the magnet is lined up with the A in the A prime coil. If we wanted to see magnetic flux, we would need it to be perpendicular to the A and the A prime coil. So if it was rotated 90 degrees either to the left or to the right, that's when we would have the maximum amount of flux passing through our A coil structure. And then as it spins, we are going to see that the flux decreases. And essentially it's a cosine relationship because we just have simple oscillation here, okay? So our flux is constantly going to be increasing until it hits its maximum value, decrease, then the flux is going to change direction until it hits its maximum negative value, and then it's going to keep spinning around like that, and that's going to happen for all three phases. And so what we're going to see is that that rotating magnetic field and that varying flux linkage will induce voltages in the stator windings. These voltages will have the same magnitude. For what it's worth, they will have the same magnitude because there's going to be the same number of turns in the A phase coil, the B phase coil, and the C phase coil. But they will be phase shifted by 120 degrees because of the physical separation of the windings. So on the A phase, I'm going to have an induced voltage of whatever my maximum electromotive force, that's just a fancy word for voltage, is, times the cosine of omega t plus 0 degrees. On the B phase, I'll have E max cosine omega t minus 120 degrees volts. And on the C phase, I'll have E max cosine omega t minus 240 degrees, which for what it's worth is the same thing as E max cosine omega t plus 120 degrees. So we have 120 degrees of phase separation, which is exactly what we would expect in a three-phase generator. Yes, Brock. Exactly right. So we haven't talked whether or not this guy is wound, the stator for a synchronous machine. But if I'm remembering correctly, and I believe that I am, I believe the all synchronous machine stators are wired as a Y connection. So these would be our line to neutral voltages. So we're literally about to get to that. Like literally the next thing I'm about to talk about. So the magnetic flux that's passing through our device, which is related to how much current we're passing through our field windings, will in turn have an influence on the value of the voltage that is generated. Okay. So passing more current into our field windings will indeed generate a higher voltage and therefore for the same amount of current, a higher power. Okay. So the peak voltage in any phase of the three-phase stator windings will be E max is equal to omega. So this is the speed at which we rotate. So we get larger voltages if we rotate our rotor faster. N, which is the number of turns in any given winding, times phi b, our magnetic flux that's passing through the air gap, which is indeed related to the current being carried by our field windings, okay? So this is what our equation would be if our winding were in a single slot, okay? But that's not usually the case. That's how I've drawn our stator because I'm incapable of drawing our stator in any other way. But more likely, we are going to have our coils distributed over multiple slots. So some of you guys came over to Neskin Hall to talk to me about motors and stuff a couple of weeks ago. And I showed you those windings and they are distributed over the entirety of the rotor section, right? Or the stator section. So in that case, what we're going to have is omega n times phi b times what's called kW, where kW is our winding factor of the stator. So this is what our relationship looks like for a winding distributed over multiple slots. And we could write this as 2 pi f n phi b kW, where once again, n is just our number of turns. Phi b is our flux per pole due to our field current IF, and kW is our winding factor. And this will always be some number less than 1. What was that, Brock? Phi. Yeah. Yes. Exactly right. So it's just the same magnetic flux that we were talking about way back at the beginning of this class when we were dealing with magnetic circuits. Flux is the magnetic field lines that are passing through essentially our core. So this thing, for what it's worth, is literally just a big magnetic circuit, right? So you don't have to write any of this stuff down that I'm about to write on here just pictorially. But so we have essentially a electromagnet here in the center. I've got the North Pole on top and the South Pole on bottom. So that's going to drive some magnetic flux up through that air gap. And then that magnetic flux is going to split. Some of it's going to flow to the left like so. Some of it's going to flow to the right like so. And then it's going to come together and flow back in through this way. So we have a coil that's generating that flux, and then it's passing through the other coils, inducing voltages. So this is exactly the same thing as the mutual induction problems that we were talking about in the first part of this class when we were looking at magnetic circuits and transformers and all of that kind of stuff. The only difference is that coil in the middle is now rotating. So the thing that's generating all of the flux in our system when we have a generator like this is the rotor. And as it rotates, the flux seen by coils A, B, and C is going to change, which means we're going to induce a time varying voltage due to that change in flux linkage, right? Because we learned much earlier in this class that our induced voltage is related to the derivative of the flux linkage with respect to time, which is essentially going to be the same thing as n times the derivative of flux with respect to time. Or actually, that would be, no, sorry, I had it right there. N times the derivative of flux with respect to time, which is the same thing as L times the derivative of I with respect to time. Again, we've had all of these relationships in this class before, so there's no need to be writing these down. You should, I hesitate to say know them by this point, but you should at least be able to admit, oh yeah, I've seen them before. Okay. So while it looks different, this is the exact same stuff we've been doing this entire class. Okay. So from this relationship, we can see that the induced voltages that are produced by our generator are dependent on three quantities, right? So they are dependent on our speed of rotation, whether we count that as an angular rotation omega or a linear frequency f, either way. It's dependent on the speed of rotation. Let me write this down. So the voltages induced in the stator windings are dependent on three things. And then number one, what we just mentioned, the speed of rotation. So that would be expressed as either omega for angular rotation or f for linear frequency. The flux generated by the field windings. Phi B. And lastly, the construction of the machine. And this is through both the number of turns as well as our winding factor. So, as a quick example, let's say that I had a two-pole three-phase synchronous generator. That is correct. Has a rotating flux of phi b is equal to 51.6 milliweber. The number of turns in each phase coil is N is equal to 20. If the shaft speed is 3,000 RPM, and the stator winding factor is kW is equal to 0.96, I want us to determine the RMS phase voltage of the generator. Root mean squared. So so RMS, the letters stand for root mean squared. This is a tangent. You guys don't need to write this down because you should have learned it in Ron's class. And if you didn't learn it in Ron's class, then we covered it in 280. You can find it on my shitty YouTube channel. Okay. So just as a quick aside. Do what? Because it's associated with my Louisiana Tech email address and all of that kind of stuff, I don't want.
There's no room for me.
Anyway, so just as a reminder for any, okay, so let's say I'm doing this real quick just because that some signal x of t is a periodic function. Okay. So just to be clear, Brock, do you remember what periodic means? Describe what periodic means, Brock. It repeats itself at regular intervals. Okay. So a sinusoidal function would be an example of a periodic function, but it could be a series of rectangular pulses. It could be triangular pulses, whatever. As long as it repeats itself at fixed intervals, it is a periodic function. The effective value of a periodic function, which is the RMS value of a periodic function, is equal to the square root of one over the period multiplied by the integral over one period of the square of the signal. So what this mathematical operation entails is that we are taking the square root, so that's where the root comes from, of the arithmetic mean, that's just a fancy word for average, of the square of the signal. So root mean squared literally just describes the mathematical operations we're doing to our periodic signal to get its effective or RMS value. So what this RMS value means is this is the same DC signal that generates exactly the same average power as our periodic time varying signal generates. So it is not it's not truly a DC representation, meaning we're not like rectifying an AC signal and converting it to DC. It's just an equivalent DC signal that delivers the exact same amount of average or real power. Okay. Exactly right. So that's why we have to square the signal itself, because the average value of a periodic function would, or excuse me, a sinusoidal function would absolutely just be zero, but we know that the average power delivered by an AC sinusoidal voltage is not zero. Otherwise, these lights wouldn't be on, my laptop wouldn't be charging, et cetera, et cetera, et cetera. Okay. For what it's worth, and we're about to use this, which is why I'm reminding of it, reminding you of it, pardon. If x of t is a sinusoidal function, so let's just say of the form xm cosine omega t plus some phase angle theta x, or xm sine omega t plus some phase angle phi x. So it doesn't matter if I express it as a sine function or a cosine function. X effective is just our magnitude divided by the square root of 2. So anytime I have a sinusoidal function, if I know what its peak value is, I just take that peak value, divide it by the square root of 2, and that is my RMS value. We are going to use that relationship here in just a moment, once I get back to that example problem, which is what I'm doing now. So, yeah.
So VRMS divided by square root of 2.
Exactly right. And so what we're about to figure out from this equation right here is what the peak value of the voltage is. Okay. So coming back around to this example problem, okay, how would we go about figuring out what our angular frequency is? Okay, so we need to know either what omega is, or we need to know what F is. We know that the speed of our shaft was 3,000 RPMs, right? So our angular frequency, omega, is just going to be the speed of our shaft, 3,000, I'm going to write this out as revolutions per minute. Well, each revolution is 2 pi radians per revolution. And in 1 minute, there are 60 seconds. So if we look at these units here, revolutions cancels revolutions, minutes cancels minutes, and we're going to have something expressed in radians per second, which is exactly what we're looking for when we have omega, okay? So just for the sake of argument here, and I'll call this omega m, anytime that we're given a speed in RPMs, if we want it to be a speed in radians per second, we just multiply by 2 pi over 60, 100% of the time, okay? So 3,000 times 2 pi over 60 comes out to be 314.159 radians per second, or 100 pi radians per second. Okay. So from here, the maximum value or the peak value of our induced voltage is going to be, so I'm just scrolling up here to get the equation. So I'm going to use that one in the middle because we have omega. So it would be omega n phi b kW. So that would be 314.159 radians per second times 20 turns times 51.6 times 10 to the minus 3 Webers. What's a Weber again? You guys remember from the very beginning of class?
I wouldn't know if you're having like 12 hours of sleep. So you can't ask anything like that.
Well, I wasn't asking you specifically, I was asking everybody. Weber. volt second, absolutely right. A Weber is just a volt second. And then our winding factor is 0.96. So if we look at our units here, we have radians, which is a dimensionless quantity, so it doesn't matter. Turns, which is a dimensionless quantity, so it doesn't matter. We have volts times seconds divided by seconds, so the seconds cancel each other out, and we're left with volts. So the units work out to where we don't have to do any conversion or anything like that, okay? And so what we would wind up getting here, let me throw this into my calculator. $100 times 20 times 51.6 times 10 to the minus 3 times 0.96. I got 311.244 volts. And so ERMS would just be E max over the square root of 2. Exactly right. So E max is the peak of our time varying voltage. RMS, because we know it is a sinusoidally varying voltage signal, we would wind up getting 220.083 volts RMS. If we had a permanent magnet, would we have control over the amount of flux? Okay, because some motors definitely do use permanent magnets, but not these. We need to be able to control the amount of flux that's flowing through so that we can generate specific values of voltages and all that kind of good stuff. Yes, what's up? So, our omega here would be 100 pi. So our or so the linear frequency. So what's 100 pi divided by 2 pi? 50. So this would be operating at 50 hertz, which would be, so we would be generating effectively European voltages with this particular machine. Yeah. So our rotational speed for our rotor would be expected to be 3,600 RPM if we were trying to use this as a generator here in the States. That is correct. We control the flux. So let's go back to those three things. The voltages induced in the stator windings are dependent on three things. The speed of rotation. So however fast we spin it also influences the size of the voltage that we generate, but how fast we spin it is going to set the frequency of how it oscillates 100% of the time. So if we have a two-pole machine like I've drawn, however fast we spin it in hertz is however fast or what the frequency of the output voltage is going to be. It is a one-to-one thing for a two-pole machine. Okay. The flux generated by the field windings, which is dependent on the current that we pass through the field windings, is also going to influence how large our voltage is. But it is not going to have any impact whatsoever on the frequency because it is a DC current, right? So we have a DC magnetic field, so a constant magnetic field that is rotating around. Okay. Lastly, the construction of the machine, so how many turns we have per phase, as well as whether or not those coils or windings are distributed or all lumped together, are also going to have some impact on the magnitude of the voltage generated. But the only thing that's going to have an impact on the frequency of the voltage generated is how fast we spin our rotor, where our mechanical speed, omega m, will be the exact same as our stator frequency, omega s.
Basically, this is actually a question I've had for a long time, it's pretty cool to see an answer. So basically, how power plants do it is they basically keep the speed of rotation constant, and then to get the actual voltage they want, they just modulate how much DC power they're sending through the coil inside.
Correct. Yeah. So,
It's all power.
so the frequency will not change based on power demand or anything like that. Yeah. So they can so it is a huge balancing act. Okay. So you're talking about the generation side of things, right? So essentially, and we'll get into this in a little bit, we have this three-phase generator, and it is going to be capable of generating some amount of complex power, right? And we'll get into those relationships and all of that kind of stuff, hopefully later today if you guys don't distract me too much. So probably next Thursday because we have our test next Tuesday. But anyway, so we can generate some amount of complex power depending on what our motor is rated for, which depends on the size of the wires and the windings and all of that kind of good stuff like that. But anyway, so if we wanted to increase our overall power output, we would need to increase the energy that's going in, right? So that could be, this also has to deal with the load that we're seeing as well, right? So essentially our voltage is fixed at our output for the most part. We just need to figure out how to make sure we're passing more current down the line. Okay. So that is going to be related to the flux, which is again related to the field windings, or the current flowing through the field windings. Okay, so let's look at our equivalent circuit for this guy. So this is going to be very different than what we had for an induction motor, okay? So on the left-hand side over here, I'm going to put what's called my field circuit. And so this is literally what our rotor looks like, okay? So I'm going to give myself some terminals here. So this is where I'm going to apply my field voltage, which is a DC quantity. I'm going to have an adjustable resistance. So that's a resistor with an arrow through it. So this is just a rheostat or a potentiometer, just a variable resistance. That is R subscript ADJ. Then I'm going to, goodness, I did not mean to jump to that page. My apologies. Then I'm going to have the resistance of my field windings. And then here I have my reactance of my field windings, JXF, and I can change the amount of current that's flowing through my field windings for a given field voltage by adjusting that resistor value. Okay, so that potentiometer is what's going to let me establish some fixed amount of flux passing through my stator. Okay, so this is the field circuit. This is a DC circuit. Okay, and I'm going to put a note here. This JXF is responsible for our rotating field, okay? On the right-hand side of the screen, I'm going to have my armature or stator circuits. I'm saying circuits plural because there's going to be one circuit for each of the three phases, okay? They are going to be identical to each other. So really, we are only going to need to know what's going on with one of them, but I'm going to draw them all for the sake of argument, okay? So my A phase circuit might look something like this. So this is my induced voltage, EA, and I'm going to treat this as if it is an RMS phasor. Okay. Yeah, that'll be fine. Here is some resistance R sub A, some reactance JX sub A, another reactance JX sub AR, and these are the output terminals. And so this voltage right here, I'm going to call V phi A. And so this is the voltage that we would have access to. This is where we would connect our load. And so I'm going to represent that by just drawing a box over here on the outside that says load. I'm going to have two more identical circuits like this. The only difference that we're going to see is that instead of having EA and V phi A, I'm going to have EB and V phi B because it will be for the B phase, and then EC and V phi C for the C phase. So to hurry this up a little bit, I'm going to be a jerk and copy this. Settle down. Yeah, I mean, I don't care if you bother drawing these other ones. I'm just trying to be complete.
So they related, they're all, they are all the exact same.
They are the exact same thing. So let's talk about why they're the exact same thing. So what we have on the right-hand side of the circuit, let me put a dashed line here just because these kind of butt up against each other, right? So everything to the left of this dashed line is our field circuit having to do with the rotor. Everything to the right of the dashed line, the dashed pink line is our stator circuit or stator circuits, where there is one circuit for each phase. So John just asked, are these really the exact same circuits? And yes, they are going to be the exact same thing, except that EA is going to be leading EB by 120 degrees and leading EC by 240 degrees because the physical separation of those coils are 120 degrees out of phase. So it's going to have the exact same resistance. It's going to have the exact same reactance because those coils are manufactured to be as close to identical as possible to make sure that the magnitude of those voltages are as close to identical as possible. Okay.
Just make sure that, but total reluctance and stuff, it's gonna be the same, the RA, JA, and the JAR, it's gonna be the same.
Yep, for each phase, they will be the same.
So it's not given A because it's A.
Correct. That is not given an A because it is the A phase. That is correct. So I'll talk about what those things represent here right now. Okay. So RA represents the AC resistance of the stator winding. Okay. This value is approximately 1.6 times larger than the DC resistance. Of the winding. Okay. Does anybody know why? It isn't square root of 2 for what it's worth. Nor is it a square root of 3 because this is a three-phase thing. Have you guys ever heard of what's called the skin effect? So this is another tangentially related thing, okay? So you don't have to write this down or anything like that. I'm not going to ask you any questions about it. But if I have a wire that is part of a DC circuit, so let's say that there's a current I flowing down the wire, right? My current is going to distribute itself over the entire surface area, cross-sectional area of the wire, okay? So essentially, all of the current uniformly distributes over the entire cross-section of the wire, and so the wire just has some fixed resistance. In an AC system, if we have that same wire, but I pass a current I of T is equal to Im cosine omega T through this wire, instead of the whole surface of the wire being utilized, only a part of it will be. So my current is only going to flow on the outer part of this wire. None of it is going to flow in the middle. And the higher my frequency is, the more current only flows on the surface. So the middle part of the wire becomes completely and utterly unused. That's why at very, very high frequencies in electrical circuits, we don't use wires at all. We use what are called microstrip transmission lines. So they are thin, flat traces on your printed circuit boards and all of that kind of stuff. They're behaving as wires, but we get to use really thin strips of wire because we know that all of the current is just going to flow on the surface anyway. So there's no point in making thick wires or anything like that. Okay.
So what is something like tiny little copper wires inside?
Yep. We don't need big wires. It's completely useless if we're passing high frequency signals. Okay. So even at a low frequency of 60 hertz, which is what our transmission and distribution systems are set up here in the States for, we are going to see some amount of skin effect, right? It's dependent on the material and it is dependent on the frequency, okay? So for copper wire at roughly 60 hertz, the resistance is going to be 1.6 times larger than the DC resistance because we see about 33% less of the area of the wire, the surface area or the cross-sectional area of the wire being used to actually carry current. Okay.
I know that like power line wire, I think they're braided.
Stranded, yep.
But still, also is it partially than this?
Sorry, yes. So you are 100% correct that in a in a DC power, or excuse me, an AC power transmission line or something, it is not going to be a solid conductor wire. That is way too expensive. Instead, actually, most of the time it's going to wind up being aluminum, but anyway, but it is stranded wires put together, but each of those strands are still going to have skin effect behavior. So our current is going to distribute among all of those strands, and then even that is going to distribute just to the outer surface of the wire. It's not going to penetrate all the way through the middle because it's not a DC.
So each wire that's like wrapped in there, it each has like current going through it.
Mhm. So what allows AC to travel a lot farther than DC? I probably should have talked about this more in the 280 class. We're getting a little bit out of sorts, but it'll be okay. So the reason why we use AC distribution systems instead of DC distribution systems is because we can transform AC voltages from a low voltage. So on the generation side of things, typically speaking, we're talking about 30-ish kV. When we are doing AC power distribution over very long distances, that may be stepped up to somewhere in the ballpark of 500 kV, okay? So the reason why we would step that voltage up so much is because if we step the voltage up by a factor of 50 or so, we're stepping the current down by a factor of 50, right? Because the energy going into the primary side of the transformer has to be approximately equal to the energy flowing out of the secondary side. Really, the energy in will be slightly greater because of losses that we've talked about in this class. So if our current flowing through the transmission line is smaller in amplitude, the ohmic or resistive losses we're going to see due to the resistance of the wire will be less because those losses are I squared R losses. So if I is smaller, the amount of power that we lose transmitting it over long distances goes down. So that's why we use AC for transmission. Easy to step it up using transformers, no power electronics or anything like that are necessary. It's just simple. You have some fixed number of coils on the primary side and a lot more coils on the secondary side, or a lot more turns of the coil on the secondary side, which allows us to step up the voltage, step down the current. We see less losses. It's more economically efficient. And then we don't step it down again until we get to where we're interested in, right? So when we like driving from Monroe to Vicksburg, you'll see those really, really large towers and all of that kind of stuff. So those are hundreds of kV transmission. When you get into Vicksburg, they're going to step that down to maybe 50 kV. And then when you get into like residential and commercial areas, that'll be stepped down to 13.5 kV at a substation. And then when you get to homes and businesses, that 13.5 kV is stepped down once again to 240. Okay. Going back to what the little symbols in our schematic diagram mean. So RA is our AC resistance for our winding, okay? It is larger than the DC resistance because of the skin effect, and I've talked to you guys about that a little bit. XA represents the self-inductance of the stator windings. And then XAR represents the effects of armature reaction. So armature reaction is simply we are going to have some armature current. Did I label them? I did not. So let me go back up here to my thing. So I'm going to have an armature current here, IA, an armature current here, IB, and an armature current here, IC. So these are literally just the currents that are induced by that rotating magnetic field that will flow whenever we have some load connected, right? Well, those currents are out of phase with our DC field. So essentially, there's going to be interaction between those magnetic fields. And we just quantify that as armature reaction. And this XAR is just our way to model that in a circuit. So it's going to just be related to how the stator magnetic field and the stator flux interacts with the rotor magnetic field and rotor flux. So it's going to look like something, and we call it an inductance because it's 90 degrees out of phase with the voltage. So the two reactances XA and XAR are often combined into a single synchronous, sorry, I can't spell for shit today, synchronous reactance X sub S, as literally it's just as simple as adding them together. So XS will be XA plus XAR. And from this, we would have a per phase armature equivalent circuit. So I'm just going to call this guy right here E sub I, where I want to be clear here. The subscript I just means I don't care if it's the A phase, the B phase, or the C phase. It's all going to look the same to me. Okay, so I'm just giving it a generic subscript. So this is RA J X sub S in this case. And then here's our terminal voltage, V phi I. Again, it could be A, B, or C, whatever floats your boat. Here is I sub I. And then once again out here, we have our load. So using this equivalent circuit, we can see that our induced voltage E and our terminal voltage V phi will be different, assuming a load is connected. So this is just from using good old Kirchhoff's voltage law. What we'll see is that our terminal voltage V phi is just going to be our induced voltage E, again, not worrying about phase, minus I times RA plus JXS for loads with a lagging power factor the magnitude of V phi will be less than the magnitude of E. This is because a larger field current is required to keep our terminal voltages constant. This is what we're going to call over-excitation. For loads with a leading power factor, we should see that our terminal voltage V phi will be greater than our induced voltage because we have a smaller field current needed to keep our terminal voltage constant. This is under excitation. The angle between E and V phi is called the power angle or the torque angle. And we're going to have lowercase delta will be equal to just the difference of the angle of our induced voltage minus the angle of our terminal voltage. Okay, I think this is a good place for us to stop for today. My hand's getting tired. We've gone on plenty of tangents. We've covered plenty of materials, etc.